Hello dears, here we will discuss the modeling of electromechanical system. The electromechanical system is a combination of electrical system and mechanical system, where the electrical voltage will be supplied to electrical circuit and it will result in mechanical output or mechanical rotation. Now the transfer function will be generated for both electrical and mechanical. So we are going to consider for this system its input is electrical and its output is mechanical. The DC motor is the element or the device which will be modeled here as electromechanical system. The DC motor is considered as actuator which converting the electrical signal to mechanical signal. It's having advantage. That's why we are using it and we are considering it in this lecture. Its torque is high. It's having high torque. Speed is controllable. We can control the speed, and its portability is good because it's light in weight, so we can carry it and we can connect it to many of the applications such as robot. We can use it for tape drives, printer, machine tool, radar tracking system, and many other systems. So this is the schematic of DC motor, where we are applying electrical voltage to its input, and the electrical voltage will allow current to flow in the electrical part of it or electrical system with it, which will end up with rotational at the output. For the rotational, it's going to be considered as inertia at the output. We will see it in the next slide. So here is the system or the DC motor, which the result of our model going to look like this. The input is a voltage, the output is theta, and in between we are going to put the transfer function which representing the motor. So let us develop the transfer function of the electromechanical system or of the DC motor. So if the armature current flow through the coil of the induction motor, it's going to result in a force. That force is to be calculated as a B into L into IA, where B is the magnetic field, L is the length of the conductor, IA is the armature current. Now, due to the rotation, there will be a voltage generated, voltage E generated. That voltage is to be calculated as B into L into V, where V is the velocity. Remember, we are going to allow current to go to the motor. Motor will rotate. The rotation will result in a voltage, which is calculated as I'm showing you here. The voltage I discussed earlier called back EMF. So the back EMF by equation can be written as seen here in this equation, where VB is equal to KB into d theta by dt. Now, what is KB? KB called back EMF constant, and d theta by dt is equal to omega m, or the angular velocity of the rotor. To develop the transfer function of electromechanical system, we are going to start with the electrical part of it. So if the voltage applied to the input of the circuit, voltage is going to cause current IA flowing, which will be the armature current. We are expressing the system in S domain, or we consider the system in Laplace domain. We will find by the application of Kirchhoff voltage law will result in IA into RA, which is this voltage, plus IA into LAS, which results into this voltage, plus VB, the back EMF voltage, equal to EA, equal to the voltage applied. And this is equation number 1. Now, I have to keep the component which linking the mechanical element to electrical element, which is going to be the torque. So, torque is proportional to current. If I will write it as an equation, it's going to be written as a Tm equal to Kt into Ia. From there, we will consider Ia, or we will calculate Ia equal to 1 over Kt into Tm. This is equation number 2. Before I go to the next, now I am going to develop the equation of mechanical system. The mechanical part going to be this one. So where the torque is applied, the same torque we calculate just now applied, and it will result in theta m, while the inertia and the damper is connected. So let us see in the next slide how to develop the equation of the mechanical system. So now let us write the equation of motion for the mechanical part of the electromechanical system. So the equation of motion can be written as you see here, where Tm is equal to the total impedances into theta m. It's 1 degree of freedom. This is going to result in equation number 3. Now, if I substitute equation number 2 and 3 into 1, I'm going to get this equation. Now, we know that LA is much smaller than RA. That's why we will neglect LA. This is a kind of approximation to the equation for a matter of simplicity. So if I neglect LA, the equation is going to look like this. Rearrange the equation for theta m over EA, because the equation shown just now has theta m and EA. We can rearrange the equation for theta m over EA. We are going to get this equation, which actually it's the transfer function of the electromechanical system. Luckily here, in the electromechanical system, the transfer function is ready. We don't need to develop the transfer function. So the transfer function will be always as you see here, which in the form of this K, means constant, divided by S into S plus alpha, into S plus another constant. So always it's having this format. Now, we need to know that the transfer function is always having the same shape in electromechanical system, here in this motor, except we need to know the value of these constants given here. Like I want to know what is Kt, what is Ra, what is Jm, what is Dm, and so on. So that's what will be seen in the next slide. So in the evaluation of the mechanical constants, it's similar to what we did earlier. Mechanical constant, by looking at this motor, we will understand, or we will catch it. We are having the motor by itself having its inertia and its damping effect due to the bearing. It's having inertia and damping. That's for the motor. We call it JA and DA. Motor is linked through a gear to the mechanical system. We are looking at the mechanical system as JL and DL. Now, to get the equivalent inertia and the equivalent damping, we are going to reflect these elements to the motor and find the total. So we will find that Jm, which to be used in the transfer function, this is Jm, which J equivalent actually, it's Jm, J motor, which to be used in the equation given earlier, it's one of the constant in the equation, can be calculated as we have discussed earlier in the rotational mechanical system with gear. Similarly for Dm. So that's how we can evaluate the mechanical constant. For the electrical constants, I come direct to the point. So the equation of torque can be written as you see here. I didn't show the derivation. It's just direct to this equation. So the equation of torque can be written as you see here. Now, the equation is linear as you see. If I try to plot the equation, it's going to give me this, what we call torque speed curve. So this is the torque speed curve of the motor. How to develop this curve? Development of this curve, we are going to fix the voltage and then change omega, get the torque, or change the torque, get omega. So the voltage is to be fixed. So when the result I'm going to get, going to give me, for example, this curve, which linear. If I'm changing V, or E, the voltage, I'm going to get different curve. So this is called speed torque curve of the DC motor. From this equation, we will be able to develop the constant. How to develop the constant? Sorry. How to develop the constant? Constants are going to be developed by considering omega equal to 0, first of all, for this equation. When you consider omega equal to 0, that means this is all 0. The remaining will be Tm equal to this value, which going to be rearranged to get Kt over Ra equal to Ts or T stall over Ea, where T stall is the maximum torque can be developed at the motor, which to be developed when the motor is locked. When the motor is locked, the torque generated at that time is the maximum. We call it T stall. Okay, so now we can get the constant Kt over Ra as a 1 unit, because in the equation always it comes as a Kt over Ra. It's equal to T stall over Ea. That means this voltage, this torque divided by this voltage. Let's go to the other constant, which Kb. How to calculate Kb? We can calculate Kb if I'm considering T equal to 0 from this equation, T equal to 0. T equal to 0, when will I get it? I will get it at this point. There is no torque. The torque is equal to 0. At that time, the speed will be no load speed. We call it no load speed, which is the maximum possible speed. So when I consider T in this equation equal to 0, we will rearrange the equation to find that Kb is equal to Ea over omega no load. So now the constants are to be calculated as Kt over Ra equal to T stall, the maximum. Again, it's T stall over Ea. And if I want to calculate Kb, it's equal to Ea over omega no load. So here is example on electromechanical system. The example will show you how easy is dealing with this kind of system. It's not going to be difficult actually. In this question, he's asking us to calculate the transfer function TL over Ea. TL over Ea, where TL is located at this position. TL located at this position, and Ea is the main input voltage. Remember that the equation we developed earlier is calculating the transfer function as this theta m over Ea. Here he wants theta L over Ea. I think it's not a problem because we can create relation between theta m and Ea. Let us consider the system in the next slide and see how to proceed with it. In the system, the first thing I will evaluate the mechanical constant. Mechanical constant Jm, which equal to Ja, the inertia of the motor, plus the reflected element, means this one reflected, it's equal to JL into N1 over N2 square. Calculated, it's equal to 12. So now Jm equal to 12. Similarly, we can calculate Dm. Dm is equal to Da plus this inertia, this damper reflected. So when we calculate it, it's equal to 10. The mechanical elements calculated, or the mechanical constants calculated. Now I'm going to go to the electrical constants. Once I calculate all the constants, I will just feed them in the equation. The transfer function will be ready. To calculate the electrical constant, I need the speed torque characteristics. I need to know what is T stall. Luckily, it's given in the characteristics. I need to know what is the voltage it's given, and omega no load is given. This curve must be given in this question. The curve must be given in this question. So we will develop now the electrical constants. From the curve, we know that T stall equal to 500, omega no load equal to 50, and Ea equal to 100. Kt over Ra found in the equation as a 1 unit. So we will calculate it as T stall over Ea 500 over 100 equal to 5. And Kb equal to Ea over omega no load, which found as 100 over 50 equal to 2. Now the constants are ready. Both mechanical constants and electrical constants are ready. So now we can substitute them in the equation. You are going to find that here in the numerator is written as Kt over Ra into 1 over Jm. So Kt over Ra, I mean this part, it's equal to 5. Then Jm found in the previous slide as a 12. We will substitute here as a 12. Then Jm again here at 12. Dm found earlier as a 10. Kt over Ra found just now as a 5. Kb equal to 2. See how simple is the things. Then we will simplify after substituting, simplify, this is what we are going to get. But remember, this is theta m over Ea. I want theta L over Ea. How am I going to do it? We know earlier we found that theta m equal to n2 over n1 theta L. That means it's equal to 10 theta L, which means I can replace this value by 10 theta L, which going to be 10 theta L over Ea equal to 0.417 over the denominator. We cannot keep this 10 here. That's why we will divide both sides by 10. So divide this side by 10 will result in theta L over Ea, and that's what we want. Divide this side by 10, it will result in 0.0417 over this denominator. And this is the transfer function we are looking for. See how easy is developing the transfer function? Only calculating the constants and feed them in the equation.